between black and white.
Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and we are closer to fine because we are closer to mathematics, delving into the wonderful topic of logarithms. So, let's get to it, shall we? All right. In many exponential equations, it is not possible to easily make the base numbers on both sides the same. So what they're talking about is life is not always a box of chocolates. For example, we don't always have something nice like this where we can easily rewrite an equation, so an exponential equation, so we have the same base, right? So clearly x is going to be 3. For example, 2 to the x equals 5. Nothing we can do there, okay? So what we do is we write both sides with a base of 10, and to do this we use logarithms, okay? So the logarithm in base 10 of a positive number is a power of 10. So therefore, any positive number a can be written in base 10 as a equals 10 log base a. So let's take a look at an example, and I put the worked out thing here because it's fairly intuitive and formulaic. So they're asking us to write the following numbers as powers of 10. Okay? Well, a number is equivalent to 10 log of that particular 10 to the log of that number. So 2 we can rewrite as 10 log 2. Okay? And 20 we can write as 10 to the, I didn't say to the, 10 to the log of 2, and 20 would be 10 to the log of 20. So take a look here. Okay? And I'm sorry, in example 21 at part B. Notice that log 20 is equal to log 2 plus 1, and it's not immediately, it doesn't immediately make sense, okay? So we're immediately apparent. I think that's the word I was looking for. This is because I can rewrite 20 as 2 times 10. Well, big whoop. Well, here's the big whoop. I can rewrite 2 as 10 log 2, just like we did here, right? Times 10 to the first power, right? So that is the same base here, multiplying. All we do is add the exponents, and we get 10 to the 1 plus log 2, okay? So it's just an example of how we can use logarithms to manipulate, okay? So, quick example here, just to get used to this idea of how we can represent a number, any number, to 10 to the logarithm of that number. So, for example, solve for x using logarithms, giving answers to 4 significant figures. And I should probably fire up my calculator, which I forgot to start, but it'll be ready here in a sec. All right, so 2 to the x equals 10, okay? And I can't get the same base, but what I can do is rewrite both with a base of 10. So 10 log 2 to the x. Yes, I'm rewriting 2 as 10 log 2. And I'm going to rewrite 100 as 10 squared. Nice, huh? Okay. And so I can say that x log 2 is equal to 2, because that is equating my exponents. Now, how did I get this? Well, log 2 is an exponent raised to another exponent. We multiply them. So this is x multiplied by the log of 2. So x is equal to 2 divided by the log of 2. And just so, you know, this is the only one we'll do on the calculator. So I'm going to do 2 over log, where's my log? It's right here, control log. And if you don't put a base, it automatically defaults to base 10. You can put a 10 in there if you want. 2 divided by log 2, and we get 6.644 to 4 places, I believe is what they asked for. Is that right? To 4 significant figures, not 4 places, 4 sig figs. Okay, so that's 6. Let's see, x is approximately equal to 6.644. Okay. What about part B? 1.12 to the x is equal to 3. Well, again, let's do a base 10. 10 to the log of 1.12, all to the x power, is equal to 10 to the log of 3. Okay? So then what do we get? Same thing, raising a power to another power, so we get x log 1.12. X multiplied by log 1.2 must be equal to log 3 because we have the same base. It's all about that base, X equals log 3 over log 1.12. So x is approximately equal to, and then we would just crank that in the calculator. I'm not going to waste the time to do that, to 9.694. Okay? All right, so next are our logarithm laws. These, it's just like your laws of exponents. Logarithms are another form of exponents, okay? So for example, if I had a to the x times a to the y, it's equal to a to the x plus y. So if the product with the same base, I add. If I have a to the x over a to the y, that's equivalent to a to the x minus y. So just like when you divide here, you subtract. When you multiply here, you add. Okay? And log of x to the n is equivalent to n log x. And you saw that in the previous exercises. And if you want to read through the proofs here, you can pause and look through it and see the proofs of why those are true. And it's based on this relationship right here. Okay. What else did I want to say here? Log of 1 over x is equal to the negative log of x because of this right here. And log of 1 is equivalent to log of 10 to the 0. So the log of 1 is equal to 0. Okay, so let's do some stuff. I'm not sure what happened there. I missed. No, I didn't miss. Okay, yeah. All right, so write as a single logarithm. Well, we have the sum of 2 logs. Oops, 1, 2, 3. Let's get rid of those. So I'm going to use this guy right here. So log 2 plus log 7, well, that's simply equal to log of 2 times 7, or the log of 14. And you can try it here. We'll just do it, I don't know. I guess it's nice to see it on the calculator. It's not like a proof. Control log of 2 plus, you can type it in, log of 7, and what do we get? Okay, and notice how it just pops in a base 10 there. That's the default. Or we can just take the log of 14. Same thing. Okay, so just a little technology convincing, I guess. So this would be equal to log of 6 over 3, according to this law right here, which would be equivalent to log of 2. Okay, try some more. Simplify without using a calculator. We can do that. Well, what we want to try and do is get the same base, maybe get some calculation. I think you'll agree that I can rewrite log 49 as log of 7 squared, and I can rewrite log 1/7 as log of 7 to the negative 1. It's a lot of stories, baby, just say yes. Okay. And now using this logarithm law, I can move the exponent to be a coefficient. So this becomes 2 log 7 over negative 1 times log 7. Now log 7 is just a number, so same thing over the same thing, of course, is destroyed because it's equal to 1. And this becomes 2 over negative 1 or negative 2. If you want to see these on the calculator, you can go ahead and pause and try it yourself if you want to convince yourself. Don't have to, but maybe you would like to. Okay. Logarithmic equations. Logarithm laws can be used to help rearrange equations. They are particularly useful when dealing with exponential equations. So all they're asking us to do is to write the following as logarithmic equations in base 10. Okay, so I have y equals a cubed b squared. So I'm going to take the log of both sides. And again, if I do not write a base, then it is base 10. So I'm going to say log y equals log of a cubed b squared. Okay, and I'm just going to use my laws here. And I'm going to say log y to break it down as much as possible. So I have the product of two things. So I'm going to use this law right here. Log of xy equals log x plus log y. So this would just be log a cubed plus log b squared. And I can further simplify it by writing the exponents as coefficients. And so I end up with log y equals 3 log a plus 2 log b. Done like a bun. Okay? So you need to be able to easily manipulate back and forth between logarithmic form and exponential form. So here for part B, we have y equals m over, let me do that better, m over root n. So I know that root n is equal to n to the 1/2 power. So I'm going to make that substitution immediately when I write this. So I'm going to take the log of both sides. So that's going to be equal to the log of m over n to the 1/2 power. And now I'm going to use this law right here. If I'm dividing two things, then I can, taking the log of the division of two things, and I can rewrite it as a subtraction. So log y is equal to log m minus log n to the 1/2 power. And then I'll use my exponential law there. Log y is equal to log m minus 1/2 log n. Booyah! All right, let's see what's next. Maybe we're going to pause here. Let's just do this one, then we'll pause. Maybe we'll only need 2 videos. So, any number can be written. Here, let's go back here because I think it's easier to follow along with this in front of us. I'm going to copy this. I should have had it here before. I'm sorry. Right? So, it says right here, the logarithm in base 10 of a positive number is its power of 10, right? So, log base 10 of d, what that means is that d is equivalent to 10 to the 2x plus 1 because the logarithm in base 10 of a positive number is its power of 10. And we have the logarithm in base 10 of a number, so it is equal to its power of 10. So that is where that comes from. So what do we do from here? Easy peasy pumpkin pie. So we just use our rules of exponents, right? So d would be equal to, let's see, 10 squared is 100, right? So 100, and that would just be to the x power. No, let me do this. So I could rewrite this as 10 to the 2x times 10 to the first power, which I won't write to take care of this, which I could rewrite as 100 to the x times 10. So now it's written without logarithms. It is an exponential equation. So now log n we have here is approximately equal to 1.301 to the negative 2x. So by the same logic, I can say that n is equal to 10 to the 1.301 minus 2x. Say yes, say yes. So that means that this is equal to, or I guess I should say approximately equal to 10 to the 1.301 times 10 to the negative 2x, which is approximately equal to 10 to the 1.301 over 10 to the 2x. Say yes. 10 to the 2x. Right? And so 10 to the 1.301 is approximately equal to, if you took 10 to the 1.301 on your calculator, this is perfectly fine right now, is 20 over 10 to the 2x. So I have my equation written like that. All right, we'll go ahead and take a pause. We'll check in with the tunes closer to fine. And before I sign out, ooh, we need some volume here. All about the bass and the volume. Yep. Very nice. Hope you enjoyed it. Let's do some more. I am...